So in exercise 945, instead of moving a leaving group from one place to another, we're going to be moving pi bonds from one place to another in a carbon skeleton. Okay, well, we're going to follow this procedure as similar as to previous procedures we've used. If you see a double bond, you should think, what can I do with that? I can do an addition reaction. So we know that we're going to have to do an addition reaction. Because if you compare the double bond in the starting material with the product, you'll know it's not there. You'll notice it's not there anymore. Another thing you'll notice is that you don't have a double bond in one place in the reactant, you do in the product. Well, how do you form double bonds? You create double bonds by doing elimination reactions. So, before we were thinking in terms of leaving groups, now we're thinking in terms of pi bonds. Addition reactions get rid of pi bonds, and elimination reactions form pi bonds. So we're going to end up doing both of those in this exercise. So we'll take our original molecule, and we know we have to do an addition reaction in order to get rid of that pi bond that we have here. But what do we want to add? Anything we add, we want it to come off of the molecule because we don't have any sort of substituents on the product. We don't have a bromine, we don't have an OH, right? We don't have any sort of weird branches coming off of that molecule, so anything we add will want to leave. That means we only want to add a good leaving group. Well, the halogens are great leaving groups. So why not add a halogen? Now you know 3 ways to add a halogen. You know hydrohalogenation, you know halogenation, and you know halohydrin formation. So those 3 ways. Oops, BR2. So you know those 3 ways. Well, which one do you want? In this first case, we'd only have 1 leaving group, which seems good. It would be easier to get rid of that. In the second case, we'd have 2 leaving groups. That would be a little trickier here. And in this case, we'd have a bromine and an OH. So again, we'd have 2 leaving groups, so that's tricky. Because we don't want anything on the molecule, we want to get rid of anything we put on. And so that will be harder in the case of these 2 bottom recipes, because in that case, we would have to kick 2 things off the molecule. In the case of hydrohalogenation, we only have to get the halogen off of the molecule. Okay. Now, anytime you do hydrohalogenation, you have to think whether you want it to be Markovnikov addition or anti-Markovnikov. Where do you want the H to go? Well, you always want the leaving group to go toward the double bond that you want to make. After all, it'll be that leaving group that allows you to create the double bond. So the double bond that we want is sort of in the ring, so we want the leaving group to be as close as possible to that. In other words, we want the bromine to be here, and the hydrogen to go on the other carbon. Okay, let's phrase that in another way. We want the hydrogen to be on a carbon that is primary, and the bromine to be on a carbon that is tertiary. Okay, let's phrase that in one more way. We want the hydrogen to be on the less substituted carbon. Well, that is Markovnikov addition. Markovnikov addition is when the hydrogen adds on the less substituted carbon. So we don't want to add peroxides here. We just want to add HBr. That will give us this Markovnikov addition. If we added a peroxide like ROOR, that would give us anti-Markovnikov addition. The hydrogen would go on the more substituted carbon, which is not what we want. Okay, well that doesn't give us our product. No problem. I'm going to erase this hydrogen because it's implied in that skeletal structure. If you look at this molecule, you will see that you have a leaving group, that bromine. So you can do substitution or elimination. If you look at the product that you want, the bromine isn't there anymore. That means we have to eliminate it, right? It's there and here, it's not there in the final, so it's here, it's not where in the product that we want, so we have to eliminate it. Well, if you eliminate that bromine, you could get 2 possible products. On the one hand, you could steal a hydrogen, so the carbon that has the leaving group on it, that's the alpha carbon. Each of the carbons connected to that are the beta carbons. Notice that these two are really symmetrical. There's symmetry in this molecule, and so those two are symmetrical, so they'll give you the same product, so I'm only going to consider the one. So you have sort of two beta positions. You have two places that have beta hydrogens that a base could steal. And so you could end up forming two pi bonds. Either you could form a pi bond toward the beta carbon in the branch, or you could form a pi bond toward a beta carbon in the ring. Now notice, this one that forms a beta carbon in the ring, that's tri-substituted, and the one that has that forms the double bond on the branch is di-substituted. The tri-substituted or more substituted one is the Zaitsev product, the more stable product, and the di-substituted or less substituted one is the Hofmann product. That's the less stable product. So which one do we want? Do we want the Zaitsev or the Hofmann? Well, if you look at the product, you'll see that we want the Zaitsev. So how do you favor the Zaitsev product in an elimination reaction? You use a skinny base. So that would be anything like sodium hydroxide, sodium methoxide, or sodium ethoxide. So here I'm going to use sodium ethoxide. Just mix it up. I always try to use a different one in each. I try to use a different one in these examples so that you're sort of exposed to them all. But that skinny base will end up giving you your major product as the Zaitsev product. You still will get the Hofmann product, it just won't be your major product. And so you increase the efficiency of the reaction that way. So there's just two steps in this synthesis. The first step is to add HBr. That gets rid of the pi bond, and it adds a leaving group onto the molecule in a Markovnikov way. That puts the bromine closer to where you want the electrons to be. So that's the first step, and the second step is to use a skinny base like sodium ethoxide. And that will give you the Zaitsev product as your major product, the more substituted alkene. And that's what we wanted in this exercise. Okay. So that's A. Let's use that same sort of thought process in B. And this is really similar. You'll see the analysis is very similar. We have a pi bond. That should tell you immediately, if you have a pi bond, you know that of the three big categories that we've learned so far, substitution, elimination, and addition, it is addition that you would do with this pi bond. So we know we're going to do addition, and it's that suspicion is confirmed. Is confirmed if you compare the reactant with the product. You see that pi bond is there, it's not there anymore, so you must have added something on. Now, whatever you add on, it's not there in the product because there is no bromine, there's no OH in that product. So whatever you add on, you're going to have to take it off or eliminate it. So again, we're going to do addition and elimination. We're going to combine those. Addition is a way to get rid of a pi bond. So you start with a pi bond, you don't have it anymore. Elimination is a way to form a pi bond. So you don't have a pi bond, you form it with elimination. Okay, so we have our starting material, and we want to add something. Now, as we saw in the last example, you want to add something that will be a good leaving group because it's not going to stay on the molecule. You don't see any bromines or OHs in that product. So the halogens are a great leaving group, and as we saw, it's convenient to just add one because then you only have to worry about taking one thing off the molecule. So HBr. Now we have to think about whether we want this to add Markovnikov or anti-Markovnikov. If you draw the product we would want the bromine, or the leaving group, to attach closer to the pi bond that we want to form. For it to be the leaving group involved in that elimination reaction, it has to be on one of these two carbons. So we don't want the bromine to go on the end, we want it to sort of go in the middle carbon. And then that means the hydrogen would go on the end. Now, to phrase that in terms of substitution, this carbon here is only bonded to one other carbon, so it's a primary. The bromine That carbon is on 1, 2, 3. It's counted to 3 other carbons, so that's tertiary. In other words, we want the hydrogen to go to the less substituted position. And that's Markovnikov addition. So Markovnikov addition is where the hydrogen adds to the less substituted carbon in a double bond. And that's what we want here. So to get Markovnikov addition, you would just add HBr. You would not add any peroxides. Peroxides would give you anti-Markovnikov addition of H and Br. So I'm going to erase that hydrogen. It's implied in the skeletal structure. Now that we have this, if you compare this with what the final product we want, you'll see the big gaping difference is this bromine. So that's not there in the product we want, so we have to eliminate it. Now, you could draw two elimination products here, right? If you think of the carbon that has a leaving group on it as the alpha carbon, and every carbon bonded to that as a beta carbon, notice that these two beta carbons are really symmetrical. This molecule is symmetrical, and so either one of those is the same, so I'm just going to consider one of them for the sake of simplicity. You can notice that we could get two possible products. Either you could form a pi bond to the beta carbon going down if you take one of the beta hydrogens, if the base steals one of the beta hydrogens down there, or instead of that, you could form a pi bond to the other beta carbon in the middle if you take the beta hydrogen, if the base steals the beta hydrogen over there. And that's the one we want, right? That is the product that we want. Okay. Well, analyzing these, you'll see that this double bond here is di-substituted on the left, and on the right, it's tetra substituted. The one that's more substituted is the more stable Zaitsev product. The one that's less substituted is the less stable Hofmann product. And what we want is the Zaitsev product. So the way you can favor the Zaitsev product is by using a skinny base. Here we would want to use either sodium hydroxide, sodium methoxide, or sodium ethoxide. We used sodium ethoxide in the last example. I'm going to use sodium methoxide here just to encourage you to think about different reagents, to build familiarity with different reagents. And that's it. That would give you your product. So the overall recipe, the whole synthesis for this, is first you would want to add hydrogen bromide to hydrohalogenation, Markovnikov addition. And then second, that would give you this leaving group on the molecule. And second, you just want to eliminate that to create the pi bond, the more substituted pi bond. That's the Zaitsev product. So you'd use a skinny base to create that as your major product. And that two-step process would be the whole recipe for creating this transformation, for making that happen. So that's how you can move a pi bond around by doing addition reactions to remove pi bonds and elimination reactions to create them.